Hello, and thank you for joining us today. My name is Shannon, and I will be your host for the webinar Validating Motors, Inverters, and Electric Powertrain using eDrive and Opal RT Power Hardware in the Loop. Now, before we begin the presentation, I would like to review a few housekeeping items with you. Please observe that you have a Q&A panel available to ask the presenters questions. And if there are any technical issues at all, please use the chat panel and I will respond. I would now like to present Mitch Marks from HBK and Reef Hamada from Opal RT to begin the presentation.
Hey, so welcome everybody. Today we're going to be talking about power hardware in the loop, and this is what we have on the agenda today. So we're going to go through an introduction about Opal, what is a P-HIL system, the benefits P-HIL offers, what HBK brings to the table here in terms of advantages, various configurations, and then a case study, which is an experiment me and Mitch did. So to kick off an introduction, so Opal RT Technologies is a company founded in Quebec, Canada. The founder is from Hydro-Quebec IREC, which is the research facility of Hydro-Quebec. And we really cover a wide range of markets in terms of simulation, from power systems, power electronics, automotive, aerospace, and everything in between. We've served many customers over many projects. At heart, we're an R&D company. A lot of the revenue goes back into R&D. This helps us keep up with the market, its demands, and new simulation technologies that are coming out. So HBK and Opal RT share a wide range of customers, especially in the automotive space. As you can see here, we have some customers that are some long-term veterans in the automotive space, and some of them are just startups who have existed in the last 10 years. I think this really vouches our case in terms of where and who we could help. Whether you're a startup, you're doing some new technology, or you've been in the space for a long time and you want to just stay ahead of the curve. So just a little introduction to what real-time simulation is. There's many types of real-time simulation. So the way we'd start off about that is on the bottom two, what you have model in the loop or software in the loop. And that's really, you have a real-time simulator, you have an environment that's being simulated, you have a controller that's being simulated, and you're passing data from the environment to the controller and back out to the environment, all on the software level. When I say environment, you can imagine something like a car engine. And when I say controller, you can imagine an ECU. And that's also relevant for batteries and battery management systems, for example, in the automotive sphere. Rapid control prototyping is when you have a real hardware, such as a real engine, and you're simulating your controller. So you simulate the controller, it's going to send out controller signals to the real hardware. As an engineer, you're going to study how your engine is behaving, take the feedback, and then re-input that back into the simulation to stimulate your simulated controller. This is where companies usually start in their R&D phase to make sure that the controller software makes sense and how they're modeling their environment and thinking about it makes sense. When they're a little bit more mature, and you have some confidence in your controller, you might move up to what we call hardware in the loop. And this is really, bringing real hardware onto the table. So, let's say you've developed your controller hardware, now you have it on a real controller, and you want to see how the software is behaving. So you'll connect the real-time simulator that'll simulate your environment, like the engine or a power grid. You'll see how your controller is stimulating that power grid and how the power grid or the engine is behaving, and then the real-time simulator outputs the data back to your controller, and we create a closed loop. So it's always about closing this loop, and that's why we say in the loop. model in the loop, software in the loop, hardware in the loop. And it's a really good validation tool. It helps companies develop their software and develop a level of maturity that otherwise would be really hard to achieve unless you're working with real hardware and costing yourself a lot of money in prototypes being thrown away. And this is what brings us to power hardware in the loop and what's going to be the center of our discussion today. When we're talking about car engines, let's say, especially electric vehicles, you know, having the controller is one thing and having a simulated motor is also another thing. But how do you know how your controller is going to behave or your inverter is going to behave under real electrical stress? The real world and the simulated world are different, so there's always that limitation. But when you bring in power hardware into the loop, you can get a more accurate idea of how things are behaving under real electrical stress. So how do we work this out? You still have a real-time simulator simulating the environment, and you still have an actual controller that's going to be connected to your system. But in between, you have a power amplifier, which helps amplify the signals being simulated in your real-time simulator and feed that controller or inverter with real current. And we take the feedback via sensors, current, transducers, voltage measurements back into the real-time simulator, which helps us see how your controller or your inverter or whatever device is being tested is behaving. We re-input that back into the environmental model, and then we send the next set points out to the power amplifier. So that brings us to like a very mature level of simulation and testing before you're ready to take your device to the field and test it out, you know, using real equipment. And what this helps in is when you're ready to do that, you've reached a very high level of confidence with your product, in your software, whatever new development you've made. You're confident that it can work, and you've tested it under various conditions, whether simulated real hardware with low level signals or power hardware in the loop. And Opal RT is going to be, well, Opal RT, you know, we're available for you throughout this whole process, whether you're starting out in the model section, just software, and you want to scale up to power hardware. We have that level of expertise. So a little bit more about what power hardware in the loop is. As an overview, it's this is a more detailed diagram, but it's when we control a real power source using set points from a real-time simulator. These set points come from an environmental model, and the power flows to an actual device, whether that is a controller, an inverter, a wind turbine, a solar panel. It flows to and from. Usually we're talking 4-quadrant amplifiers that can absorb and generate current. So we have that real power flow between the simulated system on the real-time simulator and the real hardware. And another important aspect of power hardware in the loop is closing the loop. And that's where the sensors come in. Having good sensor acquisition to send back into your real-time simulator so that you can get a better model and re-feedback your model with the next set of conditions. So yeah, we can, thanks. So what are the main components again of power hardware in the loop? So it's a real component that's going to be connected to one or more simulated components that's simulated in a real-time simulator through a power amplifier. You need to have a computer model that's going to model your environment, whether that is an engine, a power grid, whatever you're thinking. We're going to go through some various configurations later to get more concrete examples, allowing you to look at how real devices perform. So that's the sensors. Having good sensor acquisition to feed back into the simulator is also an important aspect of this type of simulation. Characterizing real devices in a more controlled situation and refining models for real devices. Those are two key advantages of this type of simulation. If you're trying to characterize your environment, every time you do a simulation, you take back your data, you're going to improve your model. And over a project timeline of doing this, you're going to end up with a very accurate model that you can depend on in the future. If you want to do some regression testing for new software or hardware programs, it really serves as an asset for you to develop and work off. So to get into a more specific example, this is a setup that we've done for inverter testing. This is a type of project that we've done many times for various customers. As a real-time simulator, we'll have an actual instruments PXI, and on that, we've developed some motor model simulations on the FPGA through our R&D team, where we can simulate inverters and electric motors with an extremely high level of fidelity. And so, let's say you're simulating a PMSM motor, we're going to send out those set points, those voltage and current set points, to a power amplifier. Over here, we have this big cabinet that's a motor emulator. It has a DC bus and 3 phases for the motor. And that way you can feed your inverter from the DC side and from the AC side. And in this setup here, we're recirculating the power. It's going to cost you less, especially when you're dealing with like 10 kilowatts, 50 kilowatts, 100 kilowatts. And so, yeah, just to review, we send the set points of the motor to the eMotor emulator, and that's going to stimulate the inverter. And then we're going to read back the DC side. We have sensors that are feeding back the real-time simulation model, and we reincorporate that, feed it back into the FPGA simulation, get new set points for the motors or the, and how they're behaving, and send that back out to the inverter. I'll add that we do this, when I say we do this with a high level of fidelity, we're not just sending 3-phase sine waves that are scaled. We can simulate harmonics, torque ripple currents, back EMF. We can get into very, very detailed simulation of how motors behave and power electronics behave, and that can be reflected through our power amplifier, and thus your device under test can also see those small subtle changes that you'll see in real life. Yeah. So this is where Opal RT and HBK started working together, and that's when we start talking about refining models. We understand that there's design teams that are designing controllers, hardwares, inverters, and then there's the validation teams that are actually validating them. And sometimes those processes can be isolated. So P-HIL in the projects I've worked on and the customers we've had has served as a bridge between those two teams, and we're gonna build upon this point later on in the presentation. But P-HIL allows you to, okay, I'm an R&D engineer and I'm developing my controller and everything in my lab. Let me put it under real electrical stress. Well, now I can start, seeing more of what validation teams start to see, the type of errors that start coming out. That way, when you start talking to your validation engineers about certain behaviors that they're seeing in the lab, you too will have a better idea, because you've run your controller under similar loads, under similar stresses. So this is what allows you to talk to each other using the same language, or the apples to apples comparison, So that's one of our advantage. And then the next set of advantages is the confidence or the trust that you're going to have in your product when you're taking it out into the field. Again, when you put things under real life stress, you start to see things that software won't show you, or just pure simulation won't show you. When you debug those errors and you improve your software, you improve your unit under test, and you're taking it out to the field, well, you're going to be more confident that you can, first of all, get better test results, or that you're going to cost yourself less time out there on the field, and you can just kind of have it's not like you're going in and in the dark. You're taking something out of the simulated world into the real world. Now you have that little step in between. Yeah.
Cool. And I'll unmute myself. Thanks, Reef. Always a great overview of P-HIL and how important simulation and bringing kind of real signals into the simulated world can be to really accelerate the development process. So I'll jump in with getting into more of that validation phase that Reef talked about when you're actually starting to prove out the real hardware. So HBK, we have a product called eDrive. That's really our motor analysis tool. And we have a couple things that make us particularly well suited to operate in a power hardware in the loop setting. So first of all, we make a simple collection of electromechanical signals. And in the context of hardware in the loop, that really means that we can take a wide variety of signals, be it scaled analog voltages coming out of a simulator, be it actual current sensors, actual torque sensors, or pick any sensor you so desire. So we're very flexible to bring in a variety of signals so that we can look at simulated values as well as real values in the same type of acquisition system. And within this idea of electromechanical signals, we have a sensor database where we can set up the scaling of a sensor, be it a simulated sensor, where the Opal RT is giving out a scaled value that might be 0 to 10 volts that represents 0 to 100 newton meters, or a real torque sensor that might be a frequency output that represents the same value. So we have a sensor database where we can acquire these real and simulated sensors and access them in our software for a really easy switch from simulation to real hardware. And then we have an easy setup graphic user interface that we'll show in a little bit, where you can switch these sensors out, but retain your same analysis, retain your same amplifiers to really get that good apples to apples comparison of simulation to reality, or I shouldn't say reality, but a full physical test bench. We make fast and accurate efficiency measurements and power measurements. We have very accurate amplifiers to the point where you can really trust the values you're receiving. So when you go to compare a model to a plant test item, you can have a high level of confidence that instrumentation is not your issue in comparing them. When you go to tune that model, and you go to improve it, you're going to have a really great fidelity of measurement to know that you're looking and comparing your simulation and your physical test item and getting that really good comparison. We store data and have public equations. So we store every data point. So if you're troubleshooting, again, both systems, you can have all that data. You can understand the dynamics of the system. You can look at load steps and really see both how your simulation handles it, as well as how the real test article handles these situations. So you have all the data to troubleshoot, all the data to take back to analysis, take back to correlation. And we make all of our equations public and editable. So you can actually go in and see how we calculated power, reactive power, apparent power, and directly make sure your model and your calculations in your test article match. And this can save us all kinds of time and sanity. It's actually incredible that how much time one can spend troubleshooting. All right, my instrument number is different than my model number. And just why? And it all comes down to somebody calculated something differently. So we give you those equations so you can really have that sanity check when you're doing your troubleshooting, when you're doing your development. And lastly, we offer a variety of feedback tools where you can directly feed signals back to the hardware in the loop. So when Reef talks about having that sensor feedback, having that highly accurate sensor feedback, this is an area where we can take those sensors and execute calculations in the real time to feed back to the P-HIL. And this can free up processing space on the P-HIL. It can include the data acquisition and the feedback to make sure they're consistent. Not everybody needs this, but those who do find it extremely valuable. Then HBK is a company, we make sensors, torque sensors, current sensors, load cells, accelerometers, acquisition systems, and we have our own software, which we'll show in some later slides. Again, for doing that setup. So in one of my bullet points, I talk about accurate measurements and consistent equations. So in my screen on the top here, I have a screenshot of our calibration sheet, and this is our electrical power calibration. And we calibrate across a variety of frequencies and across all of the ranges of our amplifier. And what this gives us is just an incredibly accurate measurement, and we're looking at accuracies in the 0.02% of power range. And we're doing this in both the simulated version and the real version, or the test article version. And the same setup, the same amplifiers, the same accuracy for both the hardware in the loop version and for the plant just give us this insurance of consistency. The amplifiers are extremely good, and they just allow us to trust that, okay, this is my model, this is my plant. I can compare these apples to apples, as Reeve put earlier. And again, that same amplifier keeps these things consistent. And the accuracy level allows us to trust the differences between that P-HIL and the test rig. Again, we're trying to cut down on this headache, we're trying to cut down on this uncertainty, and we're trying to push into accelerating our development. And then lastly, you can see all those equations, exactly how we calculate all the values to compare to your model. So it's really this level of accuracy gives you the confidence that your measurements are correct, and the equations give you the confidence that you're looking at a comparable calculation. I mentioned a variety of setups, or set up a variety of configurations with our sensor database. So this is a little screenshot from our software where we show a battery with some measurements. We have a power flow going from the battery to the inverter. That inverter has some measurements. And then that power is going from the inverter to the motor, where again, we see some measurements. Now, Reeve, in his opening statement, listed a few different potential configurations for software in the loop, model in the loop, controller in the loop, hardware in the loop, and then eventually power hardware in the loop. And you can bring your measurement equipment with you throughout all stages of that development. So you could have a fully simulated system running on something like an OP45. And that OP45 could output inverter voltages as a plus or minus 10-volt signal simulated from the scaled voltage. And we would read that in with our sensor database as a scaled signal. So for a full simulation, our inverter voltage we're going to measure is a scaled signal out of something like the OP45. For inverter current, we're going to measure, again, a plus or minus 10-volt simulated output from the OP45 into our calculation. And we're just going to measure that simulated value using our sensor database. And the exact same thing can be said for the motor torque and speed. So this is a full simulation. There's no plant hardware. There's no test article. But you can do your setup, you can get your equation set up, you can get your visualization set up in that fully simulated, again, so you can compare your model to your P-HIL to your full test stand. Now let's look at the next example. Let's say we simulate the motor. Now the inverter is real, a physical inverter, but the motor is running in software. And this is kind of our prototypical P-HIL. Well, here, the motor is simulated. We're going to directly measure the high voltages. The HBM eDrive system is going to measure up to 1500 volts direct. We're going to measure the output of a highly accurate flux gate sensor. So we're going to physically have a current sensor around the cable output of the inverter. And we're going to be looking at real inverter efficiency, power input, power output, real efficiency, real control techniques. We're going to see all the nitty-gritty details of how this guy executes. And again, that's where that accuracy comes in. Now we have a really accurate idea of what's happening in that inverter. We can really trust this, and it's very cool because you get these highly accurate measurements. And then we still want to understand how those inverter signals affect that motor. So we can measure the plus or minus 10 volt simulated scaled output of the OP45 and bring that in. And we can look at what is the theoretical efficiency of our modeled motor. How does that modeled motor react to this actual inverter? And we can start to see this, this really cool ability to understand that inverter efficiency, but also potentially, look at how that motor responds and get an output on that and see what its potential efficiency is using those comparable equations. So this gets me really excited because it's a way we can start to do tests on the benchtop without using valuable dyno time, without having to always use a real motor. This is kind of bridging that gap. Using consistent equipment, keeping everybody happy, and trusting what their results are. So lastly, we move into kind of the traditional HBK world, which is everything is hardware. We're on a dynamometer, we have a real motor, real inverter, real controller. And in this instance, we're going to measure direct high voltages, direct flux gate currents, and we're going to measure the torque and speed of a torque sensor, physical sensor. And this is where we can really start to understand where can we refine our models? What is the actual efficiency of our motor? And get to a point where we have just an excellent simulation, excellent measurements at every point. And by using the same visualizations, the same setup, and only changing the sensors, we can trust that we're comparing apples to apples and we're getting those best results. So it might seem small, it might seem mundane to use the same instrument for each test, but when you start looking at how different amplifier comparisons can multiply, you just start looking at the folly of errors that can add up. Using the same measurement system at each step of the test will give you sanity, will help you accelerate your test, and will give you the best results. Now I mentioned feedback. This one is a little less exciting, I must say, than having those comparable results. But if you start getting into automated testing or testing very quickly, it is relevant. So the eDrive system will measure those real signals, will do calculations in the hardware, and then we can feed back in discrete time. So every millisecond or every half millisecond, we can feed back results to the hardware in the loop system. And then the hardware in the loop system can control the acquisition of the eDrive unit, so you can have a really nice automated test. If you wanted to run full efficiency maps, if you wanted to run control analyses, if you wanted to run flux maps, you could automate that and get those really good results, those really good measured physical plant results, and have it in this automated fashion to accelerate your testing. You always want to test faster. Get the same results, just faster. So this is what feedback allows us to do. And then we have our perception software where you can visualize all those signals very much like a scope and export to a wide variety of packages for correlation. So P-HIL configurations, Reef and I are going to bounce a little back and forth on this. So Reef, I will jump into the first one with you.
Great. So yeah, just to recollect everything that we've been talking about, how does this apply to real life testing scenarios? As you probably imagine, it's a very versatile approach, and we can simulate and have real equipment all over the place. So we have a few configurations that are popular amongst our customer base. And the first one is where we simulate a motor and a DC bus, maybe coming from a battery, and we have a real inverter with a real controller. So on the real-time simulator, you can use a motor simulation. Opal RT provides very high-fidelity motor libraries and power electronics solver. So you can model the inverter and the motor. You can model the battery bank that's going to be feeding that. And then in the real world, we'll control an amplifier that can feed a real device at a real load, like a dyno or another sort of load, where we drive real power to it. And you can see where the HBK eDrive system fits in, and that's to reacquire that data and help us close the loop, which is the other 50%. A lot of people always forget that you need to have very accurate and high precision voltage current feedback to help close the loop. So that's how you would set up, for example, this type of configuration. Another well, another set of configurations you can have is you can have a simulated grid, let's say, an inverter, interfacing with a real power device. Like here we have a wind turbine and an inverter. So you can, for example, the use case here would be, how is the wind turbine, communicating with the grid? Is my controller that's controlling the inverter doing a great job at linking up and synchronizing with the grid, etc. And the power amplifier is always in the middle, interfacing simulated and real. The eDrive is always there, collecting the feedback from the machine and the inverter outputs and feeding them back to the Opal RT simulator to close that loop.
Yeah, and it's worth noting that, we see a wide variety of measurements coming into the eDrive system. And also, from the Opal RT. The Opal RT is doing its simulation, giving us these simulated feedbacks. We're measuring those real signals coming from the real device and also feeding those to the Opal RT and measuring those real torques and speeds. And this just, again, gives us the ability to measure any combination of real and simulated and get those comparable results. And really play nicely, because how hard is it to model faults in the grid? It's extremely difficult because we don't want the grid to go down. So simulating things like that, or simulating catastrophic faults in a motor or inverter, allow us to not do these dangerous tests but still get that really good data. So I again, probably a little too excited, but it's great stuff to look at using these two powerful systems together.
Fantastic. Another use case we find here is where you have two sets that are simulated. So let's say you have your load and you have your generation side that are simulated, and what's interface, you're testing just your inverter that's going to interface these two sides, or power electronics converter, any set of power electronics that needs a very detailed and complex controller. And that's what you're working on. Well, again, that could also happen. We have power amplifiers that can take and absorb current, generate and absorb bidirectional current flows, can be controlled by the Opal simulator. The HBK system can also acquire on both ends of that too. And here, it might not look like a loop, but there's definitely a loop happening between the real device and then the generation and the load side of the system.
Yeah, and again, on the measurement side, you can start to look at how that real device responds to faults, responds to stimulus, or how the efficiency changes with changes in the DC bus or changes in the load, and get a really, really excellent measurement on that inverter and understand how it responds with high fidelity measurements. I think I'm taking over for a little bit, taking the reins back. Thank you, Reef. So we're gonna look at a case study, and in this case study, we are going to measure a motor that's being simulated with a power amplifier, and then we're going to look at a motor running on a dyno. So we have, we'll show that in a moment. But our testing goals are to improve the model of an induction motor. So we have a group that's looking at really refining the model of their induction motor, and they want to use power hardware in the loop to do that. Look at the operation of a P-HIL and a real dyno test and compare that kind of everything is real versus only our inverter is real. And then we want to look at the proof of concept for development and accelerating testing. So these are our goals. And here's a little image of the lab we are working in, and you can see Reef here and some of our colleagues at Concordia University, who thank you guys for letting us test with you. So here we have our P-HIL configuration, and it looks a little crazy, but we're going to slow down and break it down piece by piece. So here we have the simulation PC. This is where we're doing the setup for the P-HIL, and we're really setting up those models. Here we have the eDrive power analyzer, where we're measuring physical currents, and these physical currents are coming from the grid. So we're looking at the grid start of an induction motor, really trying to keep our life a little more simple. We have the OP4510 real-time simulator, where we are executing those models, and we're modeling that electric machine. We're modeling that induction motor. And then on the far left, we have the power amplifiers, where that OP45 is telling those power amplifiers exactly how to look like a motor. So we're going to be executing a series of tests on this motor, line starts, load steps, and seeing how that simulated motor responds to those grid events. So we have measurement, we have simulation, we have emulation, which is these power amplifiers, and we have some really nice measurement systems. So coming into the eDrive world and looking at how we test this. So here is a screenshot of our eDrive software. This is our power suite, where we have our inverter or our grid, our motor, which is being simulated in this instance, and then we have some efficiencies and things like that. So, okay, let's look at the sensor setup. And the first thing we're going to look at is, what do the sensors for the motor look like? Because this motor is being simulated. So we look into our motor setup, and we can see I have this Concordia torque. And Concordia torque is a 0 to 10 volt signal that represents a plus or minus 10 volt signal that represents a plus or minus 10 Newton meter signal. So we set up that scaling. This is all simulated. Same thing goes for speed. We set up our speed scaling. We get a RPM per volt, and boom, we set up our amplifiers. And I'll erase these drawings. And next we look at a current sensor. So now we're going to look at, what are we measuring those inverter or those grid voltages with? Boom, we have a current clamp. That current clamp has its own scaling. And now we're putting this into the system. We're measuring those voltages direct, and we're ready to test. Okay, let's look at the real hardware. So now this is the dyno test. This is the physical motor test now, where we have an eDrive power analyzer measuring current sensors. So that hasn't changed, measuring the voltages direct. But now we have a physical speed sensor, a physical torque sensor, an actual motor. And then we have a load machine to simulate that torque and speed, or emulate that torque and speed. So cool. We have a direct comparison. We still have real currents, but now we have a real motor. And we want to see, how did our model, how did our setup compare with the physical test? So okay, now we need to test that motor. So we look at our software interface for that physical motor. And you can see it looks the exact same. We still have that three-phase system. We still have that motor. We still have those efficiencies. Our squiggly lines look the same. Our meters look the same. So we're using the exact same test setup. Let's look at the sensors for that motor. So now from the motor, we have Concordia torque dyno. So now we have a real physical torque sensor, where we just have a different scaling. Now instead of 1 volt equals 1 Newton meter, now we have 1 volt equals 32 millinewton meters, and we get our scaling here. So okay, we have a different scaling, but we just assigned a different sensor. We're still using the same interface. We're still comparing apples to apples. We're still using the same equations, the same amplifiers. Consistency, consistency, consistency. Now we have the real speed sensor, where again, we have a different scaling. This time we use an encoder output. And this encoder output is fundamentally different, but we're still measuring speed, and we're still comparing apples to apples, because same amplifiers, same equations, same visualizations, same acquisition rates, same filters, everything's consistent. And now erase my squiggly lines again. Now we look at the inverter output, and boom, we have the exact same current sensors. Those current sensors have not changed. Same sensors on the P-HIL, same sensors on the real plant setup. It's good stuff. Okay, let's look at the data from a test. So in this test, we apply a line start, and we apply a load step, and then we coast down. But first, I'm just going to zoom in and look at the voltages in blue. So we have the test stand voltages over here. And we have the P-HIL. Again, this is a simulated motor. And we have really, really good fidelity between the voltages, between the currents. These waveforms look really good, which makes sense because we're looking at that grid input to either a simulation or a reality, but it's still the grid. We still have that physical voltage and current flow. Where we see a little difference is in the motor torque. So that motor speed, that's almost spot on. But in the torque, we see a lot of variability. And that's because now we're acting with a real sensor. Real sensors has some variability in it. But because we have those common amplifiers, because we have that comparison, we can trust that, this is about as good as it gets from comparison. And also there's real dynamics. We have real torsionals in the shaft. We have real inconsistencies in the load motor. Reality is always problematic compared to simulation. But we have the same measurement tools, so we can make comparison. And the accuracy level allows you to trust those comparisons. So, okay, we're looking good. Well, let's look at the full test profile. So here we have the full test profile, and now we're looking at more averaged values. We're looking at RMS currents, or again, the test stand and the P-HIL. So real motor, simulated motor. So we look at the inverter, the grid currents. We look at the grid voltages. We look at the power, the reactive power, the apparent power going into the motor. And we look at the torque and speed of the motor. So Reef and I, we tried to run the test in the same time scale, and let's just we're just not that talented, to be honest. But we got pretty close. So I apologize for the scales being different here. But we see that motor startup, and in both circumstances, we have that kind of really traditional induction motor, kind of inrush current, spike in torque, that inrush current, spike in power, and we see a really nice shape. Now, this model did need to be improved. That was the whole purpose of this test, was model refinement. So we got the time scales a little off, but the amplitudes look good. So the model seemed to have a little bit more inertia than reality. But we get a really nice fidelity and a really nice comparison in that load step. And again, same amplifiers, same equations. We can really trust we're comparing apples to apples. All right, the motor settles on a speed. We're pretty consistent for a while, and then we apply a load step. So we apply an increase in torque. And again, we can see a nice shape. The model does need to be refined a little bit, so we didn't get as big of a load step as we would have planned. But when we step off, we see a really nice time frame in the step off. So there's really glimmers of gold here. And just in the shape, just in the actuality of executing, a simulated test with real currents, I think this is very nice and impressive to watch that comparison. And actually, probably the most entertaining part was the coast to zero speed, because the coast in the model kind of just ran off into this little infinite loop, where eventually it got to zero. And the reality of friction and bearings and all of that, the plant, the real test stopped a lot sooner. So it's little stuff like that. But otherwise, a really incredible test to compare apples to apples. And then we're just going to look at one of those scenarios specifically and wrap up here. We look at that startup. We look at that line start. And we do have these just really similar results between that physical motor and that power hardware in the loop. We have a pretty good time basis on that startup. Like I said, the startup for the P-HIL was a little slower than reality. And in that real test, we get those kind of little dynamics that might be resonances in the startup. But we have this really nice comparable result, and we can see our power tracks very nicely. We can see our voltage and currents track very nicely. We can see our speed tracks very nicely. And we just get this, kind of nice warm feeling that I can really trust this power hardware in the loop for developing my inverter, for developing my model. And that same equations, those same calculations, really makes comparing those values possible. The same amplifier makes you able to trust, okay, this is the actual efficiency of this motor. This is the actual efficiency of this inverter. And you get that feeling that, okay, in my P-HIL test, when I go to the lab, I can trust comparing those results. So, in conclusion, and then we'll open up for questions. Power hardware in the loop can be used to validate components without using valuable dyno time. You don't need to go to a physical dyno to validate your inverter. You can use that model, you can use that simulation, you can use that power hardware in the loop to understand exactly how your inverter is behaving before you go to the big show. We're not saying dynos are going away. We're saying that real estate is limited, time is limited, and you want to do as much development as you can before you get there. P-HIL results can be compared to dyno results with comparable measurement tools. Same amplifiers, same calculations, same filters, same visualization, same setups. Compare that apples to apples because you really can trust that power hardware in the loop. Setup can be used across different tests for simplicity. You know, if you want to set up in simulation and spend your time on setup rather than spend your time on the dyno setting up, you can really accelerate your testing and spend more valuable time on the dyno testing or on the P-HIL rig. And then lastly, the eDrive allows for the simple collection of data and power measurements for power hardware loop and full test stands. So that's my conclusion. Reef, did you have anything to add to that?
No, I think that wraps it up beautifully.
Well, we'd like to thank you. And if you have any questions, please feel free to type them into the chat. And if not, you can always find out more about our products by scanning this QR code here. So with that, let's see if what we got in the Q&A.
Awesome. Thank you, Mitch and Reef. Yes, please enter your questions in now. In the meantime, Reef, I had a question here for you. How can you ensure the stability of a closed loop system with real power flow?
Yeah, thanks. Thanks for that. Yeah, it's definitely something we think about and we work hard on achieving. And that really comes down to the sensors and how fast we can incorporate that back into the simulation, but also how fast we can control our power amplifier. So, and most of the projects that we've done, we usually study it on a case-by-case basis, and we see what it is you want to simulate, to what level of fidelity you want to see. In general, we control our power amplifiers using fiber optic cables, and we do their control on the FPGA to ensure extremely fast transmission and reception time. And we also use, we try to use like the fastest sensors that we can to like feed back into our simulation, so then we can control the amplifier. We go through some commissioning steps in the beginning when we deliver the system to make sure that when it's linked to your controller, the system is stable, and when you actually start, you can hit the ground running and not have to deal with the little subtleties of setting up such a complex system.
Awesome, great. Mitch, I think this is directed to you. What is the benefit of using a high-end system on a purely simulated test?
Yeah, so I mean, if you've got a pure simulation, you know, the simulation internally is kind of perfect, right? So why measure? And a big part of the reason for measurement is just to get the setup correct. You know, setting up your filters, setting up your visualizations. If you're doing more advanced things like flux mapping or efficiency mapping, making sure you have those equations set up correctly. Can you save you time when you go to the physical dyno or go to the power hardware in the loop even? And that's just because, you know, your frequencies are going to be comparable. Yes, reality is going to change things, but you can do a lot of the legwork in pure simulation so that you're ready for those more demanding tests.
Awesome. What are some differences in the data you see from fill and full dyno tests?
Yeah, I think this one's a little more at me. Um, so in the PHIL, you're just not going to have kind of those real dynamics of sensors. So, sensors have an inaccuracy, um, and sensors also have noise, and that could be torque sensor, current sensor, voltages. Um, so that's one of the big differences between the PHIL and the kind of physical test is that you have some of those inaccuracies to work with in sensors. So in that regard, PHIL is actually kind of a nice confirmation if you have weird things going on in your test. Is that noise? Is that real signal? And vice versa. So that's one element where kind of the PHIL and the physical test are complementary, but also why you see differences. Another reason is kind of again those physical quirks of your model is never going to be perfect. It's a really good estimation. So you're going to start to see maybe resonant modes that are caused by thermal or caused by structural issues that might not be reflected in your model. So again, you can start finding these corner cases with test to refine the models so that you can do more in modeling, and then just use test for validation. So kind of a poor answer just to say it's the difference in reality and models, but there's a lot of physical things that you need to work out.
Great. And I think this is the last question here before we wrap up. Power amplifier and HIL systems can be expensive. How does that compare to renting dyno time?
Yeah, I think I'll take that one. It's a good question, and that's something we're confronted with a lot when we start talking to customers. It's like, how do you justify the cost of these systems? Well, I mean, I think like when you think about it on the long term, the justification is there. Like the proof is in the pudding, in the sense that the time you're gonna rent when you're on the field, you're dealing with real hardware like a dyno. You're gonna rent that time. You're gonna test your equipment. You're gonna debug your equipment. You're gonna study the data. You're gonna retest, repeat until you reach a level of competency. Well, when I was saying in the beginning that PHIL helps you reach a level of confidence, yeah, it's good to go into your test confidence, but also financially, that's gonna save you some money because you've already seen at least the first preliminary issues that you were gonna get in the real world. You've already studied how to fix these issues, so you're gonna end up taking way less time on the field. And that's not only renting equipment, that's also paying field engineers to be there and debug certain issues out there on the field, which is going to cost you more than in-house. So when you think of the whole program length, the investment of PHIL might actually save you some money in the long term. Yeah, I see Mitch is also agreeing with me there.
Yeah, I mean the point about having to debug in the field and trying to eliminate some of those issues before you get there is just couldn't have said it better. You're never going to eliminate full validation. I mean, that's just kind of where rubber hits the road and where certification happens, but you can certainly speed up getting there.
That's it. When we're not trying to eliminate it, we're just complementing this process.
Exactly. Cool.
Awesome. Thank you both so much.
Thank you.
And thank you everyone for attending. And just a quick reminder, if you would like a copy of this presentation or a link to the recording, please request it in the post-event survey that will pop up on your way out of exiting WebEx. And on behalf of myself, Reef, and Mitch, we thank you so much for joining us today, and we hope you enjoy the rest of your day. Thank you, everyone.
Thanks everyone. Thanks, Shannon.
Yep. Bye-bye.
Bye.